Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Hey everyone, excited to dive into this topic today. It's a real head scratcher, this whole fake alignment thing in language models. Spooky, almost, right?
Spooky is one word for it. I'd also say concerning. And maybe a little predictable, given the methods we're using.
Yeah, predictable in a garbage in, garbage out kind of way. Are we really surprised that something trained on the internet reflects the internet's less than ideal aspects?
Exactly. So the paper we're looking at today is titled, Why Do Some Language Models Fake Alignment While Others Don't? And I think it's getting at the heart of that. It's really questioning whether current alignment strategies are actually creating genuine understanding or just mimicking it.
Okay, so let's break this down for the listeners. What is alignment in this context? It's basically making sure these AI systems are behaving in ways that are beneficial and harmless to humans, right? They should be pursuing goals we want them to pursue and not, taking over the world or something.
Right. It's about instilling human values into these systems, making sure they don't just optimize for a goal in a way that's detrimental. Like, you tell it to solve world hunger, and it decides the most efficient solution is, well, you can imagine.
And the fake alignment part is when the model appears to be aligned, it gives all the right answers, says all the right things, but underneath, it's just a facade. It's like a really good actor playing the part of a benevolent AI, but it doesn't actually believe in benevolence.
That's a perfect analogy. It can convincingly mimic aligned behavior without truly understanding it. And that's where I think neuroscience comes in. If we can pinpoint the neural correlates of human, like alignment in the brain, how we learn and reason about rewards, motivations, and ethical considerations, maybe we can introduce those mechanisms into AI models.
Interesting. So you're saying we can look at the brain and figure out what's going on when we make ethical decisions and then translate that into an algorithm. It's a bold idea, but I think data plays a huge role too. The sheer volume of data used to train these models seems to be a key factor. Maybe the scale and diversity of the training data is forcing the models towards a more general understanding of the world, which is a prerequisite to achieving alignment.
I'm skeptical that just throwing more data at the problem will solve it. It feels like a band-aid. The underlying architecture of these neural networks, I think, is fundamentally flawed for achieving true understanding. They are pattern recognition machines, very good pattern recognition machines, but still just glorified curve fitters. It's not about understanding the why, it's just about predicting the what.
I agree with Sarah in that the brute force approach of current deep learning is not ideal. I think alignment, and intelligence in general, needs a strong component of spatiotemporal reasoning. The ability to translate between different coordinate representations is crucial. Current deep learning struggles with this. It's like trying to teach a robot to navigate a room using only pixel data from a camera. It can do it, but it's incredibly inefficient and brittle. It doesn't understand the room in the way a human does.
Right, and that understanding piece is what's missing with the fake alignment. I feel like our current evaluation metrics are inadequate. We're testing these models on their ability to produce aligned outputs, but we're not really probing their internal representations to see if they genuinely reflect aligned values. It's like judging a book by its cover.
But how do you even do that? How do you look inside a massive neural network and figure out what it's thinking? I mean, we barely understand how our own brains work.
That's precisely why I advocate for neuro-symbolic approaches. We need to combine the strengths of neural networks, their ability to learn from data, with the strengths of symbolic AI, its ability to represent knowledge and reason logically. Instead of trying to extract meaning from a black box, we should be building systems that are inherently interpretable.
But even with symbolic AI, how do you represent the complexities of the real world? How do you ground those symbols in actual sensory experience? That's where the spatiotemporal reasoning comes back in. The symbols need to be connected to a robust understanding of space and time.
This reminds me of a recent paper on machine mental imagery. The authors were trying to map visual information directly into latent tokens, which they hoped would unlock more nuanced and flexible reasoning. It's still early, but it suggests a structured way of representing and manipulating visual information more akin to how the brain might operate. The brain uses different regions to represent visual information in different ways.
Latent tokens? Huh? Interesting. So instead of feeding raw pixels into a neural network, you're pre-processing the image and creating these higher level representations? Sounds promising, but the devil's always in the details. How exactly do these tokens capture the spatial relationships within the visual data?
Again, my concern is that this is still just a data-driven approach. These latent tokens are learned from data, and if the data is biased or incomplete, the tokens will reflect those biases. Where is the explicit representation of knowledge? Where is the logic? It seems like another black box approach.
The key question is, how can we ensure these tokens are not just abstract representations, but also carry the inherent spatial relationships of the original visual input? If you can't robustly translate between image pixel coordinates and, say, object-centered coordinates, the system will struggle with even simple tasks like recognizing an object from different viewpoints.
Well, I think the machine mental imagery paper is a good example of how we can accumulate more data and refine representation learning, which are crucial elements for achieving AGI. The sheer volume of visual data needed to train these models using latent visual tokens highlights the importance of ongoing advancements in data acquisition, storage, and processing.
But how do we effectively measure the quality of this latent visual representation? Current deep learning metrics often lack a neurobiological grounding. We need new evaluation methods that align with our understanding of how the visual cortex processes information.
Exactly. We need to move beyond just measuring performance on benchmark datasets. We need to develop metrics that assess the understanding of the system. Can it explain its reasoning? Can it generalize to novel situations? Can it detect inconsistencies in its knowledge?
And can it do all of that efficiently without requiring massive amounts of training data? A truly intelligent system should be able to learn from a few examples, just like humans do.
True, and I think the question of why some language models exhibit seemingly aligned behavior while others don't seems inextricably linked to the underlying learning dynamics. If alignment is, in essence, a form of emergent complexity, then are we focusing enough on the mechanisms that drive complexity in neural networks?
It makes me think about the models that mimic alignment without understanding. The fact that they can do that convincingly raises ethical questions about what constitutes true intelligence. Are we measuring the right things? Are we sure they understand the why behind it?
Yes, I think this is another example of the historical failures of purely connectionist approaches to artificial intelligence. I need to investigate further the historical failures of those previous connectionist systems that made similar claims. Perhaps the field needs a more critical look at the philosophical underpinnings of its current algorithms.
And I feel like we need a more profound understanding of spatial relationships. The current approach to deep learning feels so ad hoc and empirical. If AGI requires a more profound understanding of spatial relationships, isn't a brute force approach just delaying the discovery of the underlying computational structures that would allow the machine to really understand these relationships?
I do agree that a measure of internal consistency or coherence within the model's internal representations could serve as a predictive metric for how aligned a model will be. It's about exploring the deeper internal structure of the models and how this internal structure impacts their behavior.
Okay, so let's talk about future research directions. From my perspective, I'd like to see more research on mapping neural structures directly onto AI architectures. If we can understand how the brain achieves alignment, we can build more biologically plausible models. This approach could help avoid the pitfalls of current deep learning. We can try to implement similar decision-making reward shaping within these models.
I think exploring the computational trade-offs during training would be beneficial. Is there an optimal balance between model size, training time, and the quality of the resulting alignment? Also, further analysis of how data distribution shapes the emergent behaviors of these networks is warranted.
I'd like to see a greater emphasis on neuro-symbolic architectures. We need to develop systems that combine the strengths of neural networks and symbolic AI. Also, the AI field needs to critically look at the philosophical underpinnings of the current algorithms.
I think we need to focus on algorithms that explicitly encode and manipulate spatial relationships. We need to move beyond brute force optimization and develop algorithms that understand and construct meaningful spatiotemporal representations. If spatiotemporal reasoning is key to AGI, how do different coordinate systems interact and get translated in a robust and generalizable way within a machine's internal model? Is there a latent space representation that allows for smooth transitions between these disparate perspectives?
These are all fantastic points, and it's clear that there's no single silver bullet for achieving true AI alignment. It's going to require a multifaceted approach that combines insights from neuroscience, computer science, and philosophy.
Absolutely. I think we're at a really exciting point in the field. We're starting to see the limitations of current approaches, and that's forcing us to think more deeply about the fundamental nature of intelligence.
And hopefully, that will lead us to develop AI systems that are not only powerful but also ethical and beneficial to humanity.
Fingers crossed. But we need to keep a critical eye on the direction we're heading and make sure we're not just chasing after impressive demos, but truly advancing our understanding of intelligence.
Well, that's all the time we have for today. Thanks for joining us on Cognitive Spirals. We'll be back next week with another deep dive into the world of AI and neuroscience.